Hello. So we are still in Unit 4. We are looking at contextual applications of differentiation, and today is related rates. Yesterday, we started to introduce the idea of related rates, but today we're going to finish it out, take it over the home stretch. So students will use calculus to solve word problems for related rates of change. For a warm-up, a hot air balloon rises vertically 40 feet. If an observer sees the balloon at an angle of 30 degrees, how far is the observer from the launch site? So think back to geometry. You might want to draw yourself a picture. So here's my hot air balloon. Here's my launch site. Here's my observer. Very high-tech picture here. A hot air balloon rises vertically 40 feet. Here's my 40 feet. The observer sees the balloon at an angle of 30 degrees. Remember, that's my angle of elevation. Remember angles of elevation and depression. How far is the observer from the launch site? So that's the question that we're looking for. This goes back to trig. Remember our friend SOHCAHTOA? I'm dealing with the opposite side and the adjacent side. So that's tangent. So the tangent of the angle is equal to the opposite over the adjacent. So in this case, the tangent of 30 degrees is equal to the opposite, which is 40, over the adjacent, which is the unknown. I have a question mark in the picture, but I'll use an X here. So tangent of 30 equals 40 over X. Now, you should be able to solve this with no problem. I am going to say the tangent of 30 degrees. I'm going to come back to that in a quick second. I am going to multiply both sides by X. So X tangent 30 degrees equals 40. I'm going to divide both sides by tangent of 30. So 40 over tangent of 30 degrees. Yes, you can put this in your calculator, but this is good practice for not putting it in your calculator. Recall special right triangles. So 30 degrees, the other angle up here is 60 degrees, you have your 90, and the sides are 1, 2, square root of 3. So tangent is opposite over adjacent, so it's 1 over root 3. So this is 40 over 1 over root 3. Then this would become 40 root 3. Now, I jumped into a triangle, special rate triangle, and I think I just did that because that's how I learned it in high school, but you guys are all about the unit circle. So 30 degrees on my unit circle, let's talk about that too. Here's 30 degrees. The coordinates at 30 degrees are, I gotta think about this, root 3 over 2 and 1/2. Tangent is sine over cosine. So it's y over x. So it's 1 over 2 over root 3 over 2. So it's 1 over root 3. So that's how you get the same values here from the unit circle. So the answer is 40 root 3. Now, just a little side note, that's probably going to be one of the last times that you see degrees in the XY plane for us. We are going to use radians in calculus class. All right, so related rates problems. I like these. This is where we start to talk about calculus modeling real world situations. So a few guidelines for you. 1, draw a picture. 2, make a list of all known and unknown rates and quantities. It's very important to be organized for these problems. 3, relate the variables in an equation. Often this is where the geometry comes in. Number 4, differentiate with respect to time. Use those implicit differentiation rules. And number 5, substitute the known in quantities and rates and solve. So example 1, a 16-foot ladder leans against a wall. The bottom of the ladder is 5 feet from the wall at time equals 0 and slides away at 3 feet per second. Find the velocity at the top of the ladder at time equals 1. Now, yesterday I had said, well, it feels like whatever the bottom is, the top would be the same, but that's not true. If you have a constant rate on the bottom, the top actually falls faster. And it's not gravity, it's because a little change out here has a greater effect the lower we go down. So the first things first, draw yourself a picture. Let's get a new color, blue. So we have a ladder. Basically, you need a triangle, however you want to do it. We know that this is a right angle. We know that the ladder is 16 feet long. The bottom of the ladder is 5 feet from the wall at time equals 0. I'm not going to put a number there. I want to leave that as a variable. I know that the bottom is sliding away and the top is sliding down. So I'm going to go with variables X and Y. The way that I do these, anything that's moving gets a variable. If it's not moving, if it's constant, I'll put the number in there. So let's talk about what we know and what we need to find. We know that the bottom slides away at 3 feet per second. So because that's the X variable, this is dx dt is 3 feet per second. We want to find the velocity at the top of the ladder. That's dy dt. Now, when do we want to find that? So the ladder is falling. It's not that it stops, but you're standing away at a distance and you're going to take a picture on your phone. So you're taking a picture as this ladder falls down. So you're going to take a snapshot. That point when you're taking the snapshot is at time equals 1. Okay. So how do I relate x, y, and 16 in this particular picture? Well, I see a right triangle and some unknown sides. It's your Pythagorean theorem. So x squared plus y squared is equal to 16 squared. You can also call that c squared for the length of the ladder, but it doesn't have a rate of change, and that's how we labeled it yesterday. Now that I have my geometry, I drew the picture, check. Made the list of the unknown and known rates, check. Relate the variables in an equation, check, did that. Differentiate with respect to time. The derivative of x squared is 2x. Here's the respect to time, dx dt. The derivative of y squared is 2y, dy dt. And the derivative of 16 squared. Well, 16 squared is 264, I'm pretty sure. The derivative of 264 is 0. Truthfully, it doesn't matter if it's 264 and the other number, it's a constant. What's the derivative of a constant? It's 0. What's the rate of change, the length of the ladder? It's 0, it's not changing. Now we're ready to put in the variables that we have. So we know dx dt is 3. Actually, before I do that, what can I do to make my algebra life a little bit easier? I can divide everything by 2. So this becomes x dx dt plus y dy dt is equal to 0. Now, clearly I wrote too big, but that's okay. We'll make it work over here. We'll just zoom in. I'm going to switch colors so my work doesn't get lost. We'll go purple. So I know dx dt is 3. And I know dy dt is what I'm looking to solve for, and this is equal to 0. Now, I don't know all right. Hi, sorry about the pause there. So we are looking to find the velocity at the top of the ladder. So far we have that there are 3 feet per second at the base of the ladder. We know we want to solve for dy dt. So we need to know x, which would be here, and we also need to know y, which would be here. Now, those haven't specifically been given to us, but we can find them. So I know that the bottom of the ladder is 5 feet away at time equals 0. But this problem is about time equals 1. So we know that at time equals 1, we have to find the x and we have to find the y. Well, at time equals 1, the x is actually 8. Do you know why that would be? Well, if it starts at 5 feet away and it's traveling for 1 second at 3 feet per second, it's 5 plus 3, which gives you 8. So what you have to do is take a little snapshot to figure out what the y is. So here's a 16, here's an 8. How do you find the missing side when you're taking a picture with your phone? You would do the Pythagorean theorem. So 16 squared minus 8 squared. This is actually going to be a Pythagorean triple. I think it's going to be 4 root 3. So 16 squared minus 8 squared. I'm going to take a square root. Instead of bouncing back and forth between screens, I'm just going to hold up my calculator. I have 13 and some decimal. Remember, the AP exam needs accuracy to 3 decimal places. So 13.856. So our x is 8. Make sure you get it in the correct spot. and your y is 13.856. Now you have to solve. So 24 divided by my answer, and I have dy dt is a negative 1.732. Units are important with these, feet per second. Couple questions. Why is it negative? It's negative because it's going down. Yes, it's negative because it's getting smaller. That distance of the height is getting smaller. Therefore, it has a negative value. If we did this entire problem at, say, 2 seconds, we would have a different rate. If we did it at 3 seconds, you would have a different rate. So keep that in mind. It's always, always changing. These take practice. So let's talk about practice. We have a conical tank. Water pours into a conical tank of height 10 feet and radius 4 feet at 10 cubic feet per minute. How fast is the water rising when it is 5 feet high? And as time passes, what happens to the rate at which the water level rises? So conical tank, it's a cone. Is it an ice cream cone or a birthday hat? It's an ice cream cone. So here's your conical tank. And it has a height of 10 and a radius of 4. And we have some water level inside. So here's my water level. The water level is rising because water is pouring in. So what do we know? We know 10 cubic feet per minute. What does cubic feet measure? It measures volume. So this is the change in the volume with respect to time. Cubic feet per minute. We want to find how fast is the water level rising. That's actually going to be dH dt. Now, when am I taking a picture of this whole situation with my phone? When the water level is 5 feet high, when h is equal to 5 feet. So now I need to compare VH and everything else. That's the volume equation for a cone. Maybe you don't remember what it is, but it's 1/3 pi r squared h. Now, the cone is more complicated than the triangle, so we're going to jump right into it here. The problem is we have 3 variables. We have a V, we have an R, we have an H, but I only have information about the volume and the height. I don't know anything about this R. So I need to be able to eliminate R from the equation. And we are going to do that over here. I'm going to write a ratio. The radius to the height, and this is where you compare it to the tank, is 4 to 10. No matter where you are in this tank, the radius and the height will be in the ratio of 4 to 10, and that would reduce to 2/5. So I'm going to say that the radius is 2/5 of the height. No matter where we are, radius is 2/5 the height. So I'm going to replace R with 2/5 H. So the volume is 1/3 pi squared times H. Now, you're down to 2 variables, which is good news. You could do the calculus. You could take a derivative right now, but there'd be a product rule and a chain rule. I don't really want to do that. So be a good algebra student. Do more algebra. 2/5 H squared would actually be 4/25 H squared times H. So this is 1/3 pi 4/25 H cubed. Now, I'm not going to combine the 1/3 and the 4/25. You could, but you'll see why in a second, why I chose not to do that. So I've set up the problem. Now I'm ready for the derivative. The derivative of the volume equation is going to be dV dt. This is with respect to time. 1/3 pi 4/25 3h squared dH dt. The reason why I didn't multiply through is because I have a 3 on the top and the bottom. There's a 3 in the numerator and a 3 in the denominator. So dV dt is pi 4/25 h squared dH dt. Now, here's where we put the numbers in that we have. So 10 cubic feet per minute is here on the left. 4/25, I forgot my pi. Let's put the pi in. The height, that's here. 5 feet squared dH dt. So 10 pi 4/25, 5 squared is 25. dH dt, what happens with those 25s? They cancel out. going to do a little bit of solving here. So 10 over 4 pi dh dt. This becomes 5 over 2 pi dh dt. Now, as a decimal, what would that be? Let's check it out. 5 divided by 2 pi gives me 0.795. feet per minute. So that's how the water level is changing. Is that a positive or negative value? It's a positive value, so the water level is rising. Now, part B, as time passes, what happens to the rate at which the water level rises? So I'm going to squeeze in B down here. Well, what do you think is going to happen? As we go up and up and up this conical tank, what's going to happen to the rate at which the water level is rising? It's going to slow down. So we could do this whole problem again, say at 10 feet at the very top of the tank, and we'd have a different value. We could compare them. Or let's think about this for a second. As you go up the tank, the cross-sectional area is getting bigger, so the amount of water that you put in has to spread out further. Just the opposite is true. Think about when you drain the bottom of a bathtub. That's a really, really wide cone, but it's the same idea. As that bathtub gets emptier, it goes down the drain faster, or that water level, well, it goes down the drain at the same speed, but the water level drops faster because you have a more narrow cross-sectional area to worry about. So it does slow down. Example 3, a spy tracks a rocket through a telescope to determine its velocity. The rocket is traveling vertically from a launching pad located 10 kilometers away. At a certain moment, the spy's instruments show that the angle between the telescope and the ground is equal to pi over 3 and is changing at 0.5 radians per minute. What is the rocket's velocity at that moment? So with all these pictures, all these problems, draw yourself a picture. So here's my rocket. It is blasting off from this point. I have my spy, we'll give him some binoculars, is tracking my rocket. This rocket is traveling vertically from a launch pad 10 kilometers away. So that distance is not changing. So I'm going to put that in the picture. At a certain moment, the spy's instruments show that the angle between the telescope and the ground is equal to pi over 3. But it's changing. You don't want your rocket to stop midair. That would be bad news. So because it's moving, I'm going to give it a variable. I'm going to give it theta. And the height is also changing. At a certain moment, we've got all that. And it's changing at 0.5 radians per minute. What is the rocket's velocity at that moment? So again, we're taking a picture of this situation. We know that d theta dt is 0.5 radians per minute. That's given in the problem. We want to find what is the rocket's velocity. Well, velocity is distance over time. We want to find dh dt. At what exact moment are we taking a picture? Well, we're taking a picture when theta is pi over 3. So how do we relate h10 and theta? Again, our friend SOHCAHTOA, this is a tangent problem. The tangent of theta is opposite over adjacent. So before I do any derivatives, I'm actually going to multiply both sides by 10. Clean this up a little bit first. So now that I have the 10 on the left-hand side, now I'm ready for the derivative. So 10 tangent theta, well, the derivative of tangent secant squared. So this is 10 secant squared theta, d theta dt, that implicit differentiation with respect to time. And the derivative of h is 1, but don't forget dh dt at the end. Now I plug in the values that we know. So it's 10 secant squared theta, theta is pi over 3. d theta dt is 0.5 radians, I'm going to use parentheses, equals dh dt. Now, Mrs. Charnley, this is the question I always get. How do I figure out this secant of pi over 3? Remember that this is really secant of pi over 3 quantity squared. And remember, you don't have a secant button in your calculator. For everything our calculators do, they did not give us secant, cosecant, or cotangent. I'm pretty sure it has to do with domain issues, but I don't exactly know the answer why they don't. But secant is related to cosine. So this is really 1 over cosine of pi over 3 quantity squared. You can take the reciprocal of it. So remember your unit circle. So over here, pi over 3 comes up to here. Your coordinates at pi over 3, and make sure you look those up if you're not familiar with them, are 1/2 root 3 over 2. So is cosine the x value or the y value? Cosine's the x value. So this is cosine of pi over 3 is 1/2. And we have to square that quantity. So 1/2 squared is actually 1/4. And 1 divided by 1/4 becomes 4. So this is 10 times 4 times 0.5. So 10 times 4 is 40 times 0.5 is 20. 20 what? Feet. Nope, kilometers per minute. These take some practice. You're not going to get it all at once. Example 4, last one. When one train travels west towards Denver at 120 miles an hour, while a second train travels north away from Denver at 90 miles an hour. At time equals t0, the first train is 10 miles east and the second train is 20 miles north of Denver Station. Calculate the rate at which the distance between the trains is changing. Everything is moving in this picture. So let's just focus on one of these at a time. So here's Denver. We have one train traveling west towards Denver and another train traveling north. Why did I put that A? Train B is traveling away. All right, so Denver, train traveling west at 120 miles per hour. Again, just be careful how you label things. I don't want to put the 120 miles an hour there, nor do I want to put the 10 miles and the 20 miles because they're moving, it's changing. And that distance that we want to solve for is the distance between the two trains. So this distance over here. So here's Denver. Okay, so how do we relate those three sides? Well, it's a right triangle. So this is going to be the Pythagorean theorem. So I'm going to go with X, Y, and Z. You could use A, B, and C, but as I've done some reading over the last couple of years, A, B, and C are when you know you want to find a missing side of a triangle, and X, Y, and Z are when everything's moving. So A, B, and C, the beginning of the variable, beginning of the alphabet are for constants, the end of the alphabet is for unknowns or variables, things that are moving. So how do we fill out the rest of this picture? All right, so how do I relate X, Y, and Z? We relate those through the Pythagorean theorem. And while the video was paused, I took and wrote out what we know and what we need to find. So we know the speed, we know the velocity of the first train, which is my X direction. So 120 miles per hour. I said it's negative because that distance is getting shorter. dy dt is the northbound train is 90 miles per hour. That one's positive because the distance is getting longer. And dz dt is the distance between A and B. That's what we're looking to find. So how do we relate them? With the Pythagorean theorem, x squared plus y squared equals z squared. So I found the derivative with respect to time, 2x dx dt plus 2y dy dt equals 2z dz dt. I didn't put any numbers in because everything is moving here. Now, in terms of making my life a little bit easier algebraically, I can divide everything by 2. So we have x dx dt plus y dy dt is equal to z dz dt. Now we can start to put values in. So dx dt we know is negative 120. I know dy dt is 90. And we've got to figure out the other pieces. So they aren't given to us directly. And we know dz dt is what we're trying to solve for. So we have to find the x, y, and z. Now, those are given to us in the problem. And I didn't write them down the first time. So we could put them over here with what we already No, or when we need to find it. At time equals 0, the first train is 10 miles east. So x is equal to 10. And the second train is 20 miles north. So y is equal to 20. That's probably a good spot to put them. So x is equal to 10 and y is equal to 20. Now, I still have to figure out what z is. So you need to do a mini Pythagorean theorem problem. So x is 10, y is 20, and we want to know the missing side. So that's where we're going to do the Pythagorean theorem real quick. And I have 500. The square root of 500 is 22.361. Okay, so this is 22.361. So through the magic of calculators, I'm going to say 10 times negative 120 plus 20 times 90 and divide all of that by what we just had. So I have 26.83. So dz dt is 26.833, and we are in miles per hour. So that's how fast the hypotenuse is changing at time equals 0. If we do it at a different time, we have a different value. So that's 10 minutes later. So 10 minutes later, what's happening here? The picture is still the same. So we still have Denver, we still have our northbound train, we still have our westbound train. We still are talking about a triangle, a right triangle. So I still have X, Y, and Z. The northbound train, actually, the westbound train is dx dt. That's still negative 120 miles per hour. We still know the northbound train dy dt is 90 miles per hour. And we still want to find dz dt, all that's the same. When this time equals 10 minutes. Here's the problem. Our rates are given to us in per hour, not per minute. So 10 minutes is really, think about that, 1/6 of an hour. So we're talking about 1/6 of an hour. Now, X and Y are going to be different. So if I'm dealing with 1/6 of an hour and our westbound train is 120 miles per hour, so 120 times 1/6 is going to be 20. So this is traveled 20 miles. We're going to come back to that in a second. 20 miles west. And then the second one, well, let's do this. All right, so we have to talk about the distance. Where are these two trains located? And this one's going to be a little bit different. I'm going to switch colors on this one and make it pink here. That westbound train, I know, is traveling for 1/6 of an hour. And I know it's traveling at 120 miles per hour. So 1/6 times 120 is going to give me 20 miles. That's great, but it started out 10 miles east. So here's Denver. It started out over here 10 miles east and is traveling west. Well, I know for 10 minutes, it's traveled a total of 20 miles. So now it's over here. So if this whole distance is 20 miles west, it's now 10 miles west of Denver. So this isn't actually what my triangle looks like anymore. My triangle now looks like this. So my X is now over here. And my hypotenuse is up here, and this is still Y. So my triangle has changed a little bit, and that's okay. But X is now equal to a -10. So the distance is 10, but remember it's gone to the left of Denver. So X is equal to -10 miles. Now we have to talk about the northbound train. So the northbound train, I'll do this one in pink as well. It has also traveled for 1/6 of an hour. The northbound one is going at 90 miles per hour. So 90 over 6, divide both by 2, 45 over 3, 15. So it's gone 15 miles north. So here's Denver. Remember, it started out 20 miles north of the station, and now it's gone an additional 15. So now it's 35 miles to the north. So y is equal to 35 miles. Okay, that's all the back work. I'm going to see if I can save this here real quick. I'm going to shrink this, bring it over here. There it is. Okay, so let's get back to our triangle. It's still the Pythagorean theorem. It's still x squared plus y squared equals z squared. It's still 2x dx dt, 2y dy dt, 2z dz dt, but I'm going to do the divide by 2. So 2x dx dt, 2y dy dt, 2z dz dt. I've already divided everything by 2, so we're good with that. The rates are the same. I still have that negative 120. I still have the 90. So x, we said that distance is negative 10, so we're going to put that in. We said that y had a distance of 35. And z, we're going to come back to that in a second. The z dt is what we're solving for. So, you know, there's a lot going on here. You're going to have questions. Make sure you're asking them, please. So we know that this is a negative 10. We know that this is 35. We need to find the hypotenuse. When you go to square that negative 10, it becomes a positive 100. So you don't have to worry about negative values in your Pythagorean theorem. Just kind of solve as usual. So 100 squared, nope, 10 squared plus 35 squared. Square root of this gives us 30.4. So this is 30.401. All right. Negative 10 times negative 120 plus 35 times 90 divided by 30.400549 gives me 143. So dz dt equals 143.089 miles per hour. That's how the hypotenuse is changing. Now this one's positive. That hypotenuse is getting longer and longer and longer. I had an error on my last answer. That should have been a negative 26. So the first one in part A, because that hypotenuse is getting shorter, it has a negative rate. In part B, because that hypotenuse is getting longer, it has a positive rate. That was a mouthful. Sorry, this was a bit of a choppy lesson today. I appreciate your patience. You're going to have questions. You're going to have a hard time. That is okay. I want you to draw a picture. I want you to write out the know and the find. And then I want you to send me an email. I want you to ask Mrs. Oakes if you're in person. Hey, how do I set this up? Hey, do I have the numbers in the correct place? They take a lot of time. So students always tell me, Mrs. Charnley, I can get it from, you know, the derivative on down. I know you can. You know how to do those things now. I'm looking for the top piece. I want the picture. I want the know. I want the find. That's the most challenging. The calculus is easy. The calculus is easy. It's setting up the problem that's the hard part. So do your best. Send me screenshots of your picture. I'll help you out. See you later.